Alright, we just went through a couple of examples that we had to use chain rule twice. Now let's move on to examples that we have to combine chain rule and other derivative rules, particularly the product rule like A and quotient rule like B, or more quotient rule actually. Now the key here in this kind of problems are, what do we do first? Do we apply product rule first or chain rule first? Oh, excuse me, I didn't want to really give away the answer. I hope everybody can see that the outer structure of problem A is a product rule. We're talking about the first function times the second function. And that is usually the key. The chain rule started kind of like this, outside first and move inside, but that doesn't apply just to chain rule. Actually, it applies to every derivative problems. Here, outer structure is product rule, this function times that function. So outside in this case, means product rule and then chain rule. So product rule, u prime v plus u v prime. That is the structure of the product rule. And then we have to fill in these blanks as separate new problems. U prime looks like that's going to be easy, 6x plus 2. Now v prime looks like that's going to be a bit of a challenge because we are looking at a composite function, consequently a chain rule. So let's go ahead and apply chain rule. Outer function is 1/2 power function, so that comes out, nothing changed inside, and then negative 1/2 power. And then what was inside? Nothing changes there, so 5x to the third power minus log of x will just go right back in. And then we have to multiply the derivative of the inside. What is that? 10, excuse me, this should have been cubic power. So not 10, the 15x squared minus 1 over x. That'll conclude this problem. Let's see if I did it right. Let's open up this cell, and yes, everything is right. I did a little bit of color coding as well. We have first function and second function. First function in blue and second function in red. And then here in this product rule, u prime v, u prime v, u v prime. Here the derivative part I'm color coding is coming from blue. And here the derivative part I'm color coding is coming from red. And the red part here in this case was a chain rule. So it's a combination of two rules, product rule and then the chain rule. How about the next problem? Looks like this is gonna be chain rule and quotient rule, but wait a minute, is it chain rule and quotient rule or quotient rule and chain rule? What's the answer? The idea is again the same. The main idea is outside first and then inside. So you have to look at the outside function first. What is the outside function? It's square root function. So that one first, and then you have to deal with the inside, which means it's chain rule first. Here we go. And then we have to multiply the derivative of the inside. That is the structure of the chain rule basically. Just like product rule case or other cases, I'm kind of using the same convention. This bracket part stands for the derivative computation yet to be done. Of course, this convention is something only I'm using, so if you do not like it, it's fine. Or also, do not expect other mathematicians to follow me. So inside never changes, so let's just copy that. Okay, and then we have to calculate the derivative of the inside, and that is gonna be the quotient rule. something complicated. Well, let's see. Let's go ahead and do that. The denominator squared. Oops. And then here we have to have u prime and then v minus u v prime. That is the structure of the quotient rule, and then we have to fill in these brackets here. What is the derivative of the numerator? 2u plus 2. What is the derivative of the denominator to be filled in? 3u squared minus 3, I think. And I'm using the character u here, and then those product rule and quotient rule were given by u's and v's, so there was a bit of confusion there if you just read through what if you just listen to what I'm reading. But if you look at it, then you can see what I'm talking about here. Again, I use a little bit of color coding in this answer key, blue over red, and then the derivative of blue highlighted in blue, derivative of red is also highlighted in red, and then just copying part is written in black. Okay. The next problem is going to be a little bit more challenging. I'm not going to completely finish that. Okay, I don't want to show you this too much. You have to make a decision which rule to use first. Is it quotient rule first or chain rule first? It's going to be quotient rule, because the large structure, the largest part, this outer structure, is this over that. So it's going to be quotient rule. And when you calculate u prime v minus uv prime in the numerator, the u prime part will have chain rule because of this, the second part. And then the v prime part will also have chain rule because of the second part. Well, okay, I can open up the cell and show you the answer, but I'd rather leave this to exercises. As you know, this notebook is posted, so please read through the notebook and use the answer key only as a last resort. Okay, let's now move on to the next topic, the second derivative. Second derivatives are, technically speaking, very much related to the previous example, combining product rule and chain rule, and also combining quotient rule and chain rule, especially the first one. Let's begin with these two rather benign looking functions, and this exponential function is rather benign because the derivative of that is rather straightforward. We can simply apply the chain rule, and then exponential simply stays the same, inside stays the same, and here's the derivative of the inside. And I even followed, to a certain degree, the color coding. What you ended up with is the product of two functions, the blue function and then the green function. Consequently, if we calculate the second derivative, which means take the derivative once again, then what follows will be a product rule. The derivative of first function, u prime times v plus u times v prime. Again, the color-coded part means the derivatives, and then black part are just copied part. That's going to be sufficient if this had been just derivative computation problem, but let's do a little bit of simplification, because this kind of simplification is going to be necessary in chapter 4. Basically, what we want to do is factor it as much as possible. We have common factor, the exponential part, and also 6x minus 2 is a common factor. So take those out, the common factors out, and what's left here? From the first term, 6x minus 2 is left, so here. And from the second term, 6 remains, so that's what we get. And then if we do further computation, which will just have 6x minus 8. Why is this so important? if you set this one equal to 0 to find something called inflection point, chapter 4 concept, exponential is never 0, so this doesn't do anything. Second factor can become 0, so 6x minus 2 is 0, x is 6 over 2, or x is 1/3, there goes 1. And here comes the second, x equals to 8/6 or 4/3. Of course, there's another issue here. Taking the first derivative here, that one equals to 0, I'm gonna get x equals to what? 2/6. Yes, if I set this one equal to 0, that's what I'm gonna get. Now the next example is related to chain rule and quotient rule. The reason is because if you take the derivative of logarithmic function, well, what is the derivative of log function? Derivative of logarithmic function, if it is just log of x, then the derivative is just 1 over x, isn't it? But if we have a composite function, we'll have to apply the chain rule. So inside never changes, but outer structure is logarithmic function, so the inside goes to denominator. I'm talking about this specifically. 1 over that. And then by the chain rule, we have to multiply the derivative of the inside, and that's what this is all about. We are multiplying the derivative. Consequently, we have the derivative over the original function there, because multiplication to a fraction means multiplication taking place to the numerator. In short, we have this kind of extended formula, as a matter of fact. If you have derivative of u as composite function, then we get 1 over u of x from the first two steps of chain rule, outer function, and then inner function never changes. And then if you multiply by the derivative of inside, you're going to get u prime of x, and consequently you get u prime of x divided by u of x. And what do you end up with? We end up with a quotient, as we have right over here. That's very typical for logarithmic function. So if you go over to the second derivative, quotient rule comes out of nowhere, and then here it is. This kind of problem is a little bit less typical than the product rule and chain rule problem that comes from exponential function, or as a matter of fact, if we open up the trigonometric function, then, well, yeah, alright, we'll have a lot of different types of problems coming from the trig. One more quick example, and then we're going to move on. Tangency problems. Well, okay, we can find out the equation of the tangent line by something like this. The derivative evaluated at that point is the slope. x0 is given, and y0 is something you can find out from the function value. And specifically, we are talking about this kind of step-by-step process. y0 by plugging in, derivative computation, m by plugging in, and then the slope point equation of the line. Let's apply that to this problem. Okay, plugging in x equals to -1, I'm going to get y0 value, and that's going to be easy. Here we go. Now, taking the derivative by chain rule, I'm going to get, well, that. And we have seen this before, so let's move on. Plugging x equals to -1 again, I'm going to get my m value. Here we go. And then putting these all together, we have the slope point equation of the line. And then here is the graphical justification, by the way. And then we have a tangent line there at x equals to -1. If you break up the parentheses and simplify a little bit, then you're going to get slope-intercept equation. The next problem is a little bit more complicated. because of the derivative computation, but pretty similar. I'll leave that to students.